In this experiment, we're going to start to work with dry ice, and we're going to use it to create dry ice bubbles. What you will need for this experiment is some dry ice, which is, just so you know, frozen carbon dioxide. You can get dry ice at most grocery stores, and sometimes in the butcher department, sometimes it's in the front of the store. Just ask around, but this is usually sold in the grocery store. You'll need some duct tape. You will need some clear plastic tubing, and you'll see what that's for in a little bit. You'll need some kind of fitting that you can plug into this plastic tubing, and we'll talk a little bit about that later. You'll need a 2-liter bottle, just an empty 2-liter bottle. You will need Dawn dish soap or some kind of dish detergent because we are going to be blowing bubbles. And you'll need some kind of tongs to help us out with this experiment. And you'll also need, obviously, safety glasses because this is kind of a, I don't want to say it's dangerous, but you need to be careful with dry ice. And also you might need some mittens also when we're working with dry ice as well. So as you can see, there's not too many things really to this experiment. There's the dry ice, there's the tubing, there's the 2-liter bottle, and a few extra things like tongs. One thing you do not want to forget is to put your safety glasses on when dealing with dry ice. So let's take and put some of this stuff off to the side because we're going to use some of it here in a little bit. So I'll put the soap over there. I'll put the dry ice front and center for you here so we can see it. And we'll use the duct tape here in a minute as well. Before we actually do the experiment, which is blowing, carbon dioxide bubbles or dry ice bubbles, we want to talk a little bit about what this stuff actually is because it's interesting, it's fun, and also because it's, it can be dangerous. Just like anything can be dangerous, but once you know how to handle it, once you know what it is, you are well protected. So what is this stuff? It looks like ice, and it's called dry ice. But in fact, it's quite different than any kind of ice that you have in the freezer. In your freezer, you have frozen water. That's what we call ice. When you take frozen water, it's at 0 degrees Celsius. If you add heat to it, it melts into liquid. If you add heat to the liquid water, it boils and becomes vapor, gas, right? So 3 states, solid, liquid, gas for regular old water. Now this stuff is carbon dioxide. So that's the gas that you breathe out whenever you exhale, carbon dioxide. If you take carbon dioxide and put it in a super cold freezer, eventually it will cool down and it will become solid, like these guys right here. So these guys are solid chunks of, look like little ice cubes, but they're actually frozen gas. Now if you kind of notice, a little bit, if you kind of look down at it, you might see a little bit of smokiness going on here. It's not really smoke. What happens is this stuff is really, really cold. It's much colder than regular ice. And just to give you an example, regular ice is 0 degrees Celsius, right? This is negative 78 degrees Celsius. So if this is where ice is at 0 Celsius in your regular old freezer, you have to take carbon dioxide 78 degrees lower than that in order for it to freeze. So the reason it's dangerous, so to speak, is not because it's poisonous, it's just because it's so cold. If I get my fingers and start playing with this stuff and start trying to grab it and just play around with it, my fingers will actually freeze because it's colder than an ice cube, much, much colder. So I can get frostbite. I can freeze my fingertips and cause all kinds of blistering and things like that. So you never, ever, ever, ever want to touch this stuff with your hands. You have to use mittens or you have to use some kind of a tongs, which is what I'm going to do today. And you always want to wear safety goggles or some kind of protection to help you out with this. So what it is frozen carbon dioxide gas. So this is very, very cold. Now the other thing that makes it different than regular ice is that this stuff doesn't exist as a liquid carbon dioxide. See, with water, it's ice cube, liquid water, gas, which is water vapor, right? And you can go solid, liquid, gas. With this stuff, it doesn't exist as a liquid at the pressure that we live at here on Earth. So when you melt dry ice, it doesn't go to liquid, it goes straight from solid to gas, straight from solid ice cube or solid frozen carbon dioxide cube, dry ice cube, to gas carbon dioxide. And so it doesn't go through liquid. And that has a special word in science. It's called sublimation. So it's a little different than a regular ice cube. It's just the way it behaves. It goes straight to gas. Now let me kind of cut to the chase just a little bit and show you what actually happens before we blow our bubbles. I want to show you a little bit what happens when you actually put this stuff in water. So here's some warm water. Not going to put too much, just going to fill it up a little bit. And what we're going to do is just take one of these regular size cubes here and drop it in the water and see what happens. Let me actually switch this guy around here, put this guy right over here, and we'll put this guy right here. So let's grab one of the medium-sized cubes, drop it in there. And you can see that what happens immediately whenever you put it into water is it starts making this fog-looking stuff. It starts making this Halloween-looking stuff. So what's happening here is we're putting this very cold dry ice directly into a warm liquid, because I have warm water here. And so what's happening is the solid carbon dioxide is going straight from solid straight to gas. It's melting, basically. Just like if you take an ice cube and you put it in water, it melts. But ice goes from solid through liquid, and then if you heat it up some more, it goes to gas. Dry ice doesn't go to liquid. It goes straight from solid to gas. So that's why we see all the gas here. Now, if you kind of swirl your fingers around the gas, it feels a little bit cool. That's because the stuff is really cold. The dry ice is actually very cold in there. And what you're seeing here is carbon dioxide. Now, I want to make sure you understand, the fog you see, the white puffy smoke looking stuff, that's not the carbon dioxide. Carbon dioxide's invisible. I mean, think about it. You breathe it, right? So when you blow out, and you breathe in, you blow out again, you don't see the carbon dioxide. That's invisible. But the carbon dioxide, when it comes off of the dry ice cube, is so cold that that cold carbon dioxide gas is condensing the water in the air. And that's the cloud you see. So the visible stuff, the cloud-looking stuff, that's water vapor that's condensing, that's in the air. The carbon dioxide itself is very much odorless and invisible, and you can't see that. So you're seeing a mixture of the two here. Now what's going to happen is if we leave this here long enough, you can see the cube still down there in the bottom bubbling away, it's going to eventually disappear. It's going to go from a cube, it's going to disappear because all of that carbon dioxide is going to leave. Now it makes for some really fun effects because you can make these nice fog effects, and what we're going to do is use this to basically try to make some dry ice bubbles, to fill some bubbles up with this guy. That's the point of this sort of experiment here. So let me go ahead and move this over here and move my dry ice back where we started. And what I have here is a tube. This is a flexible plastic tube. It's clear. You can buy this at the hardware store. It costs a couple dollars. And I have a fitting here. It doesn't really matter what kind of fitting. I just wanted something I could wedge into the bottom of this and to give me a little bit of a wider opening. So I'm going to stick this in here. I'm just going to wedge it in there. I'm going to blow my bubbles out of the end of this, so I just want to have it a little bit larger. So imagine you kind of blowing on this end here, then bubbles are going to sort of pop out the other end. So the next thing we need to do is make our bubble solution and figure out how we're going to channel this smoky carbon dioxide water vapor mixture into our bubbles to make these really cool bubbles. All right, so the next thing we want to do is go ahead and make our soapy mixture. This is what we're going to blow bubbles with. So we'll take our dish soap and we'll just put sort of a healthy amount down on the bottom. And then what we'll do is we'll take some of our water and we'll just sort of make, just like you would blow bubbles, you know, with a bubble wand, we'll make like a little solution of that and see if we can get that to make bubbles. So what we'll do is we'll just use our little finger here to stir this up. There's nothing dangerous here. It's just water mixed with dish soap. Now you may have to play with the mixture here. You might have to play with the amount of soap that you have in order to blow some good bubbles. Now to go ahead and test it, all you do is stick it in the end there, kind of wiggle it around and blow a bubble. And we can see that we're making bubbles, so we're doing good. So we'll go ahead and put this off to the side. And the next thing we're going to do is create a way to channel this dry ice carbon dioxide into our bubbles, right? So that's what we need to do next. So what we're going to do is we're going to drop our dry ice in here. And so we need some water. So let's go ahead and put this water in here. Now this is warm water. It's not super hot. You don't want it to be super hot. You want it to be nice and warm. And you want to fill it up about halfway or maybe a little bit more. So this is about where we want it. We want water that's nice warm water, not too hot, not too cold, in about 3/4, 2/3 of the way up this bottle. Now what we need to do is figure out a way to connect our bubble blower with this. And I have a saying that in the house that duct tape can be used for just about anything, and that's what we're going to do here as well. So let's just sort of grab a nice bit of duct tape. It doesn't really have to be, you know, too tight. It just needs to be tight enough to secure this hose into the top here. So this guy's going to go in here and we're going to tape it in place. But before we actually do that, we want to get the dry ice in there and ready. So we're going to have that set aside. We're going to put the dry ice right over here. And now we're almost ready to go. We have our dry ice, we have our bottle, we have our bubble solution here. And what we're going to do last is put a little rag out. You don't want to get a nice towel, you just want to get a nice little rag that's sort of beat up and something you don't care about. Basically, when you blow these bubbles, the bubbles are going to want to stick a lot better and not pop if we kind of let them land on this little towel. So that's why we put that there. All right, so we're about ready to go. What we're going to do is we're going to drop some dry ice in here until we start to see a nice cloud form. Then we're going to stick our tube in there and duct tape it. And then we're going to start to submerge into the bubble solution and go from there. So I have a lot of dry ice here. Some are too big to fit, but I have these nice little pieces. You can kind of break it up with a hammer and drop one in there. So we'll just kind of go one at a time. You can see some are easy to fit and some aren't. So I'm just going to drop a few in there until we have enough where I think we can actually start blowing some bubbles. Okay, so we have 3 or 4 bubbles of dry ice, blocks of dry ice in there. You can see that they're rapidly releasing carbon dioxide, which is coming out. It's hitting the water vapor in the top of this guy and condensing it. That's the cloud you see. And now we're ready to actually start to try to do this, guys. So let's take our tube. We'll just put our tube in there, and we'll just take some duct tape and just make a nice little seal to force the majority of this gas to go out here. And I'm going to put one more piece just so we don't lose anything right off over the top, just like that. Again, it doesn't have to be really tight because you're not really putting a lot of high pressure through here, you're just trying to channel it. So what we're going to do next, and you can see we have our little gas coming out there. We're going to put it in there and start to blow some bubbles. And there is a dry ice bubble. We'll bounce it off, and it popped there. Let's see how big they can get. Let's just kind of hold it there and just see when it's ready to let go. And I'm going to try to let it drop down into the little soap that's dripping down above here and see if it'll detach. Almost. But you can see these bubbles are full of this this carbon dioxide gas with water vapor. There we go. So we want to tilt it to the side a little bit, and we can get them to detach and kind of land on our towel a little bit. All right, and whenever you're done looking at them, you can just touch them, poof, and there it goes. See if we can get one to stay. Sometimes they say, sometimes they don't. So basically that's what's going on here. We're taking the dry ice, we're causing it to sublimate inside, and we're channeling the carbon dioxide plus the water vapor through a tube and into some bubbles. When you're done looking at them, you can just pop them. 1, 2, 3. So it's a lot of fun. Just make sure whenever you do this that you don't cap off your bottle, that you have to have a place for the air and the carbon dioxide and the water vapor to get out so you don't build up dangerous pressure inside of this bottle. And now we're going to have a grand finale for these blowing of these carbon dioxide bubbles, or these dry ice bubbles. So before we had sort of the little bubble wand blowing small bubbles. Now we have a large bowl with warm water inside and a lot more dry ice. And what we're going to do is try to blow a bubble with the entire bowl. So here are some large pieces of dry ice. Notice what happens when I put them in. Lots and lots of action. So we'll put that in there. We'll put some more. Immediately starts to bubble. Put some big chunks in there. Something like that. All right. Now I have a piece of a rag that I've cut here. And what we're going to do is sort of put that into our bubble solution. And what we want to do first is we want to kind of get some nice bubble solution right along the edge, along the lip. We want to hold our rag out kind of flat. This is a little bit messy here. I promise it's worth it. And we'll just go around the edges, dragging this bubble across. Now you can see we formed a bubble right across the top of the bowl, and it's getting larger and larger, the pressure increasing inside from the gas that's coming up. Eventually it'll pop and should spill right over the top. So let's check that out. You can actually get these things pretty big too, if you dare, so to speak. So here we go. It's already kind of outgrown it completely. It's so tempting to actually just pop it right now, but I'm kind of curious how big it's going to get. Now this is not going to make a mess as far as the bubble part of it goes, because what it's filled with is gas. So as soon as it pops, it's going to spill over. The water and everything is still in the bottom there. So here we have almost like a little brain. You know, let's see how big we can go. And there it goes. And it just spills right off of the top. Now that was actually cool enough where we're going to do that again. We just go from here, drag it across, create the film. Now one tip I can give you when you're doing this, because it took me a few times to actually get this to work, do not fill the water level all the way up in this bowl, because it's bubbling so much inside it pops the bubble. You want it about halfway or maybe less, and then the bubbling that you hear is not impacting, you know, it's not hitting the actual bubble on the top. So there you go. And again, it's so tempting just to go ahead and pop that guy, but we're going to let it go one more time. I wish there was a way I could just blow it and have it float off, but obviously one thing that, you know, I didn't point out that's very important for you to understand is when we were blowing the small bubbles, notice how the small bubbles were sinking. The small bubbles didn't float away, they sink. And that is because carbon dioxide is heavier than air. It's more dense than air. Now, there's a couple things we want to talk about to understand the science here. We talked about dry ice. It's frozen carbon dioxide gas. Really cold, really dangerous if you touch it with your hands, so you never ever want to do that. When you put it in water, it starts to release carbon dioxide gas, which is really cold. That cold carbon dioxide gas starts condensing the water vapor, and that's the cloud that you see. You know, you can wash it away, flip it away with your hands and sort of see the vigorous bubbling here. But the cloud you see is actually the water vapor. The carbon dioxide is invisible. Now, if you remember, when we were blowing our carbon dioxide bubbles, there's a science lesson in here because you're filling it with that carbon dioxide gas along with water vapor. Now, carbon dioxide is heavier than air. It's more dense than air. So carbon dioxide is going to tend to sink instead of float. So a regular bubble, when you blow a bubble, it floats away, right? Well, with a carbon dioxide bubble or a dry ice bubble, it's actually heavier than air. And that's why all of those little bubbles, after they kind of detach, they kind of just sat there. They didn't float away because inside that bubble was a gas that was heavier than air. And that's kind of what happens here as well. You notice all of the carbon dioxide is kind of staying inside of this bowl. And if I flick some of it out like this, it kind of runs over the edge and hits the table, and it kind of just hugs the ground as it goes. And that's because it's heavier than air and it wants to go down like that. So the water vapor with the carbon dioxide wants to go ahead and follow that path. So the water vapor with the carbon dioxide gas wants to follow that path. So it's heavier than air, it's extremely cold. You want to make sure and have precautions when you work with it. Always work with an adult or a supervisor whenever you're doing this. You can get dry ice at most grocery stores. It's actually very inexpensive. It's a few dollars for a big block of it. It'll keep in your freezer for a couple days. And when it melts, there's no mess. Whenever dry ice melts, it just goes into the air. So it's not any kind of pollution or anything like that. So go grab it. Go play with it, but do it with an adult and do it with some supervision and do it with some common sense. Don't try to grab this stuff with your hands because it will burn you, it will hurt you. But there's definitely a good science lesson here, learning about gases, learning about density and the fact that the stuff in here is more dense than air, and that's why it's wanting to stay, you know, inside this container, and that's why when we billow it out, it kind of wants to hug the ground. That's an important science lesson there. And the fact that these bubbles can be blown, and whenever we blow those bubbles, they kind of sink to the ground too. So it's mostly a lesson in buoyancy and how the bubbles want to sink, along with learning about dry ice and the fact that it's frozen gas. And it does not go through a liquid phase. When you take dry ice and you heat it up like we're doing with the water, it doesn't go to liquid, it goes from solid directly to gas. That's called sublimation. I'm Jason with scienceandmath.com. I hope you've enjoyed this experiment. Go get the materials, go have fun with it, use some common sense, and learn about dry ice and blowing dry ice bubbles. Learn anything at mathandscience.com. Today what we're going to do is build a very simple battery, believe it or not, out of a lemon. It's very, very simple to do, and it's a great way to learn about what batteries are and how they work. All you need to do this experiment is a copper penny, just a regular old copper penny. The cleaner the penny, the better. You will need a nail. Now you need to make sure this nail is a galvanized nail. It's very easy to find. Just go to the hardware store, look in the nail section, read the box. Most of them are going to say galvanized. All right? And then also you'll need obviously a lemon. Just any old lemon will do. Believe it or not, these three items, the copper penny, the galvanized nail, and the lemon are just enough to make a battery. So to actually do it, it's very, very simple. First, what we want to do is put on our safety glasses, just in case, you never know. And if you're a youngster, you need to make sure and get a grown-up to help you with this part, because you will need to use a knife. So what you do is you just make a little bit of a cut into this lemon, just a little slice, just big enough to kind of insert this penny, right, until it's halfway sticking out, just like this right here, all right? And then you take your nail, and right next to the penny, you go ahead and insert it just like so. Just stick it on in there. It doesn't really matter how far you stick it in or anything. Believe it or not, you have just constructed the world's simplest battery. And it's kind of hard to believe, but it's true, because inside this lemon is an acid. You know, think of citrus fruits, citrus oranges. Well, there's citric acid inside of this lemon. And so we stick two different kinds of metals in this lemon. One of them is a copper penny. One of them is a nail. It's galvanized. That just means it's coated with zinc. Two different kinds of metals inside of an acid makes a battery. Now, we'll talk about exactly how it works later in more detail. But right now, let's just see if we've actually built anything. So what I have here is a voltmeter. Basically one of these guys, if you have one laying around, it sure does make it a lot more fun because you can measure what you've done as far as building this lemon battery here. But even if you don't have one, you can still have some fun. I'll show you how to do that in just a moment. So what we have here is our lemon battery that we've built, and on top of it I have a regular old AA battery. Now, as you know, all batteries have a positive and a negative side. For this battery, this is the positive side, the side with the kind of the thing sticking out at the top. That's always positive. Of course, it's labeled as well, positive. And negative is the other side. So when you turn this meter on to measure voltage, right, you always want to try to stick the red guy on the positive side. So when we do that, we measure, for this new battery here, 1.55 volts, 1.5 volts is what we measure here. What's a volt, by the way? A volt is just simply a measure about how much push a battery has to push the electricity out. So you can think about, you know, if you're going to send electricity out of a battery, something needs to be pushing those electrons out of the battery. And the voltage, the higher the voltage, the more push is available to send that electricity out. So what we're going to do now is see if we've constructed a battery here. We have the penny on this side, we have the nail on the other side. We'll put both terminals on, and we will see we have 0.75 volts. So we can see we do have a voltage across these two terminals of this little lemon battery that we've created. So again, this guy's a little, you know, obviously more powerful. It's got more voltage, 1.5 volts. This guy has less voltage, you know, because it's built out of a lemon, right? So, you know, you might say, well, hey, if it were so easy to construct these batteries, why don't we just make 1 million lemon trees and make 1 million lemon batteries, and they'll be basically free, right? We can just power our iPhones and iPods and computers with lemons. Well, it's not quite that easy. You know, there's a lot of things going on inside of this lemon battery that I'll explain to you here in a few minutes to teach you exactly why it's producing electricity. But for now, just suffice to say that this lemon, that the acid inside and the chemistry and everything going on inside is not really strong enough to be able to produce a lot of electricity. So even though we can measure it with this sensitive meter, it's not able to produce enough electricity to really power a typical device like a camera or a phone or anything like that. So that's why we build these batteries here with the concentrated acid inside and the materials to really make a nice powerful battery. All right, so before we get into trying to explain exactly what's going on here, I want to point out something to you that you may or may not have figured out on your own so far. This guy, for this battery, 1.5 volts, I have the red guy against the positive terminal. If I flip it around like this, then I'm going to get exactly the same voltage, but I'm going to have a negative sign. Notice here there's a negative sign on that meter, right? So if you ever see a negative sign, it just means that you flipped the direction of your measurement leads. So when I connect it in the proper way, red on the positive side, I get a positive number. That's what I want. Now when I hook it up to my lemon battery, I also get a positive number now here. What this means is that this penny is the positive terminal, just like this over here is the positive terminal. The nail of this lemon battery is the negative terminal, just like this over here is the negative terminal. Notice for both measurements, I get positive numbers when I hook them up like this. So think of it this way. When you build a lemon battery, penny is positive, P for P. Penny is positive, nail is negative. That's pretty easy, right? Penny positive, nail negative. That's the way you can really, really easily remember which side's positive and which side's negative. All right, now before we get into actually explaining what's going on in here to to see how the battery works. Let's see if we can use this battery to do something. Here I have probably the cheapest calculator that I could find, the most inexpensive, no-frills calculator that I could possibly find. And what I would like to do is see if I can use these lemons to power this calculator, because most of these calculators that we have nowadays really don't take very much electricity at all to work. If you were to hook this up to a light bulb, it wouldn't work, because a light bulb requires, believe it or not, a lot of electricity to move through that light bulb to light it up. These little electronic calculators, they don't take very much electricity, so we might be able to get it to work. So what we're going to do first is open this guy up. Now again, if you're going to do this, I recommend that you do it with the cheapest calculator you can find, something that you don't mind if it gets destroyed, because you're probably going to destroy it here. Now notice what we have on the inside here. We have a circuit board. You know, we don't care what's inside of there, but on the top we can see, notice this particular calculator, it has a solar panel. Let me turn it on for you just to show you that it does work. It's got a solar panel, right? But it also has a battery. So that means that if you're in the dark and the solar panel is not functional, the battery will power the thing. So what I'm going to do, just to make this easy, is I'm going to take my pliers and I'm actually going to try to pop this battery out. Actually, it's probably going to be easier just to pull this red wire. I'm literally just going to disconnect it like that, and I'm going to pull this other wire out and just kind of rip it out. So I don't have any more battery power anymore. These guys are not functional, but I still have the solar power. So if we flip it over and if we turn it on, the calculator still works even though we remove the battery, because we have the solar panel. So obviously if we want to make sure we're powering this guy with the lemon, then we want to make sure that we're doing that. So what I'm going to do next is take this solar panel and really carefully try to remove this guy off like that. So now we have nothing connected. Now if we turn it over and we turn the calculator back on like this, you'll see absolutely nothing is happening. So the thing is obviously not powered. We've taken the solar panel off, and we've also taken the battery off. All right, so we have our calculator ready to go. We have our lemon battery ready to go. So let's go ahead and take some of these terminals here and try to connect it together. Now notice inside this calculator, the people that built the calculator, they have a black wire that went to the solar panel, and they also had a red wire that went to the solar panel. The red wire is always associated with positive in electricity, and I tried to teach you that a little bit earlier. The black wire is always associated with negative. So we're going to use black and red here to hook our battery up. We already talked about the fact that the penny is positive, so we're going to hook the red guy up to there. And we already talked about the fact that the nail is negative, so we're going to use that guy there. Now, it's probably not going to work with just one lemon, but we'll give it a shot, because like I said, these lemons don't produce very much electricity. So I will do my best to clip this guy on here to this guy like this, and then clip this to the other side, try to clamp it down really good, like that. Now let's go ahead and gently, without disconnecting anything, turn this over and turn it on. And I've got nothing. Let's just double check, make sure everything's connected. Everything's connected on the back, but nothing's working. So why do you think that's the case? It's because of what I told you a minute ago. These lemon batteries, they can produce a tiny amount of current, a tiny amount of electric current, but not very much current. So what we need to do, much like in an electronic device you might have to put 2 or 3 regular batteries in, we're going to probably have to connect 2 or 3 or 4 or 5 or however many it takes lemon batteries together to be able to power this calculator. So let's go ahead and do that right now. Going to disconnect these guys here. I'm going to go ahead and leave these wires connected to the inside of this calculator, and I've already kind of constructed some more of these lemon batteries over here. So let me scoot the calculator a little bit to the right. Okay, everything's still connected on the back. I'll scoot it over a little bit to the right. And so here is another lemon battery, and what I will do in order to hook these things together, grab another one of these alligator connectors. Now the way you hook these guys up is much like a regular battery. When you have these regular batteries and you hook them end to end, right? You've got positive, negative, positive, negative. You go end to end and you have basically a higher voltage, okay? So we need to do the same thing here. Positive, negative, positive, negative. They have to kind of alternate like that. And what we're going to do is hook the inside guys together. All right, so we're going to hook the inside guys together. Now remember, we got about 0.7 volts out of this battery before. So now if we hook, since we've got these guys connected across the inside, if we hook the outside terminals together, we should measure both lemons together, and now we get about 1.2. It's just about double the individual voltage that we measured before. So we have a higher voltage than we did before. Makes sense. 2 lemons, 2 batteries in series, we should get a higher voltage, and that's what we get. So now that we have that squared away, let's go ahead, let's leave this right over here. Let's go ahead and connect this guy, positive terminal to red, negative terminal to black, and look at that, the calculator came alive, right? We can of course turn it off, we can turn it on, all right? And so we have 25 times 4 equals 100. And just to make sure you understand there's no trickery going on here, the only thing we have on the back here, we've got a battery that we've completely taken the wires out of. We don't even have a solar panel anymore. I've completely removed that. And so we have the power going into this guy directly connected to these lemon cells. Now, I want to make sure that you understand, though, that the only reason this was able to work is because these electronic calculators, they really require almost no electricity. They're so good at building these calculators. The batteries last forever. They don't require very much, and that's why we can power it with a couple of lemons. If you try to hook a light bulb up to this, if you try to hook a motor up to it, if you try to hook anything that requires more electricity, you're going to be disappointed because it doesn't produce very much electricity here. But it does produce enough of a trickle for these 2 lemons to power this calculator. Now what I would like to do to close the section is try to do my best to explain why, because as we've talked about before, science is wonderful, let's learn, let's do experiments, let's do cool things, but let's also try to figure out what's going on here, all right? What you have going on inside of this battery, I'll just point and gesture to this one right now. What you have going on inside of this lemon battery is you have an acid. We've talked about it. It's called citric acid, right, inside of this guy. And you have a nail that's galvanized. That means that nail is coated in zinc. That's done at the factory. That's why we needed the galvanized nail. And we have a pinion, and that's made of copper. It's really important that both of these metals are different. It makes for a better battery, and that's why we've chosen it this way. What's really happening inside of this guy is this nail is becoming oxidized by the acid inside of this battery. So you may have heard of that word oxidized before. You know, if you take a piece of iron and you put it outside, outside in the weather and let it sit there for a few months, we say it oxidizes, it turns to rust. What that means is that iron sitting outside is losing electrons. Right? And so it's losing the electrons, it's giving those electrons up to the oxygen in the air, and it forms iron oxide. That's called rust. Rust is not good. We don't like rust. You get a rusty car, not good, because rust is not very strong, right? We don't like rust. But that's what oxidation is. What's happening inside of this battery is this zinc that's on this nail is oxidizing right before your very eyes, so to speak, inside of this acid. The acid in the lemon simply provides an environment where the oxidation can really happen and do a good job of oxidation. So this zinc is losing electrons, right? It's losing electrons. That's what oxidation means. Where do you think the electrons go? Well, they're not just going to just sit there. They're going to try to go somewhere. When we hook them up in an electric circuit, the electrons bleed off of this nail, go through the circuit, in this case through the calculator, come back to the positive terminal, which is the penny. And that's why the nail is negative. The nail's negative because it's the guy donating and creating the electrons. It's not really creating them. It has the electrons inside of the nail, but it's donating them to the circuit. They go through the circuit, they come back around, and the penny is sort of trying to attract these electrons and kind of take them in. And that's what you have here. And that is the fundamental concept of any battery. If you could take this apart, this little AA battery, I don't recommend it, but if you could, you would see an acid in there and you would see metals in there. And it's the same kind of chemistry. One of these metals is donating its electrons, and then the other metal is accepting the electrons, after the electrons go through the device, through your iPod or whatever, the other side of the battery takes those electrons in, and after a while, you basically deplete the ability of these metals to create more electrons, and the battery is dead. So if I hook this guy up and leave it for a few weeks or whatever, eventually this lemon battery will actually die, and it won't be able to produce any more electrons because the chemical reaction going on here is going to stop. Once you oxidize too much of this zinc, it can't go on forever. You kind of deplete what's there, and so you can't do it anymore. That is the fundamental of battery technology. It's pretty exciting. It's very easy to do. Make sure you get a very cheap calculator. The cheaper the better, because it'll require less electricity. This calculator literally cost about $4 at the drugstore, so you can get them. 2 lemons, a penny, a zinc nail, which is galvanized nail. Hook them up in series like this and you have a nice demonstration for anybody. One more thing, depending on the calculator that you have, you may actually need 3 lemons or 4 lemons or 5 lemons. I didn't even know until I did it how many I would need. So go ahead and have a few handy and just continue connecting them in series the same way that we've done these two. And eventually you'll reach enough electricity that you can actually power this calculator. I'm Jason with scienceandmath.com. I hope you've enjoyed this. Go and get these materials, do this experiment, show your friends, and I think almost anybody would agree it's pretty darn impressive. Learn anything at mathandscience.com.